Hello everyone. Today's session is session 7 on arithmetic module in the subject computer organization. My name is Dr. Shabin Taj. Here are the contents, table of contents. We are going to discuss fast multiplication, bit pair recoding of multipliers, carry save addition of summands. In the previous sessions, we discussed about how the multiplication is performed using sequential circuit multiplier. What are the demerits or disadvantage of it? The more number of partial products were there. And using Booth algorithm, it treated both the positive numbers and negative numbers equally, and hence that drawback of sequential multiplier was removed. But still, it has a problem that the number of partial products are able to remove, or it cannot be reduced. Now we'll see using bit pair recoding of multipliers how fast multiplication can be performed. Let us see here. The multiplier is 11010. Here the two square boxes what you see here, this is initial 0, which is nothing but implied 0 to the right of LSB. Always you can take implied 0 0, implied bit for the given multiplier as 0. And how about the sign extension? Yes, whatever you have MSB, you extend the same bit over here, because we are trying to group it into a two number. I mean, a pair of earlier in the Booth algorithm, you are grouping into pair of 2 bits. Now you take a 3 bits. Intermediate step also can be used like here 0, 1 and pair it to -2. And first you can take the Booth algorithm pairs and then you again pair it to 2. So this is also possible. Let us see an example for this. Okay. Now you can see here the bit pair recoding multiplier has considered 3 bits. So the bits are I plus 1, I and I minus 1. That means it will group the 3 bits. Current bit, the previous bit and the next bit. And what you depends on those bit values, you are finding the multiplication multiplicand position. What is it 0 into m or plus 1 into m? This is what it is trying to do. Let us see the example. As I just now told you, you have an implied 0 for always implied 0 for every multiplier. So now you take and you convert the multiplier to bit pair multiplier. Now you have this initial 0. So 1 0 0. Now the pair is, can see the pair is now 3. 1 0 0. 1 0 0 is this. What you are getting? Minus 2. Minus 2. You can do minus 2 over here. Directly also put. You can take this as a using Booth table. Booth table. Okay, so I have omitted this step, intermediate step. Now take the pair of this 101. 101 pair is 101 pair is what? 101 pair is minus 1. Yes, obviously minus 1. Okay, and the pair group of three last three digits, it was 111, which is nothing but 0. Here is your number. What is this? This is a new bit pair recoded multiplier. Now originally using Booth algorithm, we used to do the thing and how many partial products it was having. If you are doing 5-bit multiplication, 5 partial products were there. 0, 1, 2, 3, 4, 5. 5 partial products are there. Okay. PP stands for partial product. PP0 to PP4. 5 partial product. Okay. PP0 to PP4. PP4. 5 partial products. Okay. Now, see here. Now, what has happened in the bit pair recoding multiplier? The same thing is now grouped into, in order to make the multiplication faster, you are changing the multiplier. Instead of this, you are taking this, which is what? How did you get 0, minus 1, minus 2? You got this from here. Okay. Now, how many partial products are there? There are only three partial products. What is three partial products? PP0, PP0 to PP2. Okay. Now you can see how you got the multiplication. How is it different from minus 2? And so you okay, observe here 0 multiplied by m is 0. Okay. Plus 1 into m is nothing but m itself. Plus 1 into m again m. Plus 2 into m. Plus 2 into m is nothing but minus 1 into m. Minus 1 into m. I write it here. Minus 2 into m is nothing but minus 1 into m and shift left. Shift left. 1 bit position. Shift left. 1 bit position. 1 bit. Okay. Similarly, plus 2 into m is what? So now all of you know what is minus 1 into m. Minus 1 into m is take 2's complement of m and shift left 1. Plus 2 into m is nothing but similarly you just is nothing but plus 1 into m and shift left. Similarly as it is said here, shift left. Okay, this is addition thing. Now how you got it here? I'll erase this and show you. Okay, so minus 2 times the multiplicand is what? So multiplicand is what? Multiplicand is your 0, 1, 1, 0, okay, 1. What is minus 2 into m is minus 1 times m. Yeah, take 2's complement of it. 1, 0. I'll write it directly. This is 2's complement of m. Now, what you're supposed to do here, shift left 1 bit position. When you shift left 1 bit position, it is like this 1, 0, 0, 1, 1. The vacant position will be filled with 0. This is your answer. Minus 2 into m. Okay, minus 1 into m is nothing but what is this? You got this. Okay, 1, 0, 0. So minus 1 into m is without shifting. My plus minus 2 into m is minus 1 into m and shift the value multiplicand left 1 bit position and 0 multiplied by the number is the 0 itself. Along with this you have to do the sign extension. The rest all same as you did in the normal booth multiplication or normal sequential multiplication. You have to do the sign extension. Since 1 was there, you do the sign extension of other bits. How many bits? Because it's a 5 bit, another 5 bits you have to do and another 4 bits. Now, what is this? What is the again advantage over here? The advantage here is the number of partial products are reduced to 2. How many bits are there? 5 bits are there. Okay. So 5 by 2. 5 by 2 is what? Now it's a integer division. So let me take it's a approximately it's not integer, it's a approximately 3 partial products are there which is there here. Okay, this is your answer. I hope this example is clear for the bit pair recoding. Let us come back to the now bit pair recoding of multipliers which was shown in the example. Okay, now you can see the same thing is given in this slide. Okay, now you can see here which how did you obtain this. I explained n by 2 multiplication requiring only n by 2 summons. This is how the multiplication becomes faster. Now we'll see another method of in order to speed up the multiplication, that is called as carry save addition of summands. CSA speeds up the addition process. How? You can see this circuit. What you see, it uses a full adder of what? 3 input full adder. And CSA can be implemented using ripple carry adder or carry look ahead adder. Obviously, carry look ahead adder is a fast compared to ripple carry adder. Okay, so this is ripple carry adder. We are not using this. We'll see now. Here we are using the carry save addition commands. Normal addition is this. Okay. Now you can see that the carry is nowhere propagated. Can you see? Carry is never propagated from one stage to another, but instead it is given to the next circuit. Okay. Now, how this carry save addition of summands is done? Group the summands in threes and perform the carry save addition on each of these groups in parallel. Parallelly it will be done to generate the set S and C vectors in one full adder delay. One full adder delay. What is one full adder delay? How much it was? It was around 5, right? Group all of the S and C vectors into threes and perform the carry save addition on them. By generating a further set of S and C vectors in one or more for full adder delay. Continue with this process until there are only two vectors left. So you have to keep on doing the carry save addition until unless you find a you are left with sorry you are left with only two vectors. So then they can be added using ripple carry adder or carry look ahead adder to produce the desired result. Let us see an example. Now go to the board. Next page. Okay. Now you can see how this is performed. Carry save addition is nothing but each partial product is stored in a separate variable. Say A, B, if partial products answers are given to the values A, B, C, D, E, F. Now you can see that how the carry save summons is done. A, B, C are added to generate a result called sum1 and C1. Here you are using a full adder of 3 inputs. So A, B, C being the 3 inputs, the sum result obtained is S1 and C1. And those are added to the next stage. We'll see that. Now DEF is also added in order to generate the sum 2 and C2. Now all this sum 2 and C2 are S1 C1 is there, S2 is there, S3 is there. All these are added. Now here C1. Now this S1, C1, S2 are added to generate a sum 3. Sum 3 is generated and C3 will be your result. Next, sum 3, C3, C2 is added to generate a S4 and C4. Let me show you here with the circuit. Okay, can I use this? Yes, I think I can use. Okay, now you can see how you got this. A, B, C are added to generate a sum 1 C1, and D, E, F are added to generate S2 and C2 as it is shown here. Okay, and then S1, C1, S2 are added to generate a sum 3. Sum 3 and C3. Okay, C2 is carried as it is. These are added to generate a S4 and C4. Sorry, there is this. Okay, and this two will be your thing, and this will be used for your final use during the addition. Okay, I hope this is clear. And carry save addition is pretty faster compared to your all other technique because it allows you to take the all the three inputs and it works for a combinational digital circuit. Okay, this is what again it is shown here. A, B, C are added to generate a sum 1 C1, D, E, F are added to generate a sum 2 C2, and it as the name says, carries are preserved. Carries are preserved in order to generate the sum. Hence, this is the end of the session 7. Here are the references. Thank you.